In the last lecture, we looked at linear system of equation comprising of two equations in two unknowns, and we could find a solution easily where it was possible and also characterize the nature of the solution. And it was easy to do so in the case of just two equations with two unknowns. Now we will learn a standard method for solving linear system. This method is known as Gauss elimination. So let me write it down. Gauss elimination. And to understand Gauss elimination, we need to first understand what are elementary row operations. So let's start with an example. Let's consider the following linear system of equations. So let's consider x plus 2y is equal to 5 and x plus y is equal to 3 and x plus y plus z is equal to 6. Since a linear system is completely determined by its augmented matrix, the elementary row operations can be performed on the augmented matrix itself. To show this one-to-one correspondence, I will write the linear system and the augmented matrix side by side. So let me write the augmented matrix here. So the augmented matrix will be the coefficients basically the coefficient matrix. So this will be 1, 2, 0 and 1, 1, 0 and 1, 1, 1, and write a bar and then write all the constant terms on the right side of the LHS. On the right side of the equality. So it's 5, 3 and 6. So this augmented matrix describes the equation on the left side completely. All right. Now, what happens if I interchange the first and the second row? Right. So if I interchange the first and the second row, the linear system of equation now becomes x plus y is equal to 5 and x plus 2y is equal to 3 and x plus y plus z is equal to 6. And the augmented matrix will now be 1, 1, 0 and 1, 2, 0 and 1, 1, 1, and put a bar, and now we will have, so I made a mistake here. So this, when I interchange these two equations, right, so this becomes x plus y is equal to 3 and this becomes x plus 2y is equal to 5. So yeah, so we finish writing the augmented matrix. This becomes 3, 5, 6 over here. So now let me ask you a question. If I interchange the equation 1 with equation 2, or correspondingly I interchange row 1 and row 2 in the augmented matrix, will the solution for this linear system of equation change? No. So both these linear system of equations will have the same solution, right? And so what it means is that the row interchange in case of augmented matrix does not really change the solution. Now let's consider one more case. What if I multiply, say, equation 2 by 2? So I multiply this linear system of equations 1 and I multiply the equation 2 here by 2. So this the new linear system will become x plus 2y is equal to 5 and 2x plus 2y is equal to 6 and x plus y plus z is equal to 6. And the corresponding augmented matrix for this linear system will be 1, 2, 0, 2, 2, 0 and 1, 1, 1, and put a bar and 5, 6, 6. So again, you'll notice that multiplying equation 2 here with the scalar 2, or correspondingly multiplying the second row of the augmented matrix with the scalar 2, will not change the solution at all. So this linear system will have the same solution as this linear system. And lastly, let me multiply equation 2 here by -2, all right, and sorry, and add the result to equation 1. So if I do that, I'll get x plus 2y and -2 times this guy, right? So x plus 2y minus 2 times x plus y is equal to 5 minus 2 times 3, 5 minus 2 times 3, and so the equation 1 becomes minus x is equal to -1, and the second and third equation we will leave them as it is. So the second equation will be x plus y is equal to 3 and x plus y plus z is equal to 6, and the corresponding augmented matrix will be -1, 0, 0, 1, 1, 1, 0, 3, and 1, 1, 1, and 6. All right. So basically you see that this again, and again you can see that this linear system, which has been obtained by multiplying equation 2 of this linear system and adding it to equation 1. So this guy here and this linear system here, they have the same set of solutions. So basically, if you add if you multiply an equation and add it to another equation, or correspondingly if you add a constant multiple of one row to the another row in the augmented matrix, the set of solution remains the same. Okay. And now, so what I'm trying to formally speak here, or trying to formally state here, are certain rules that you have already been following. So these rules you have been following all along to solve, to find unknowns, find multiple unknowns in multiple equations. So let me actually write them down formally here. So the first rule is that interchange of two equations, right? The second rule is multiplication of an equation by a non-zero constant. And the third rule is addition of a constant multiple of one equation to the other. Okay, so all these three operations, when performed on a linear system, will leave the solution unchanged, and these three rules or these three operations are known as elementary operations for equations. All right, and correspondingly we have elementary row operations. So if you have an augmented matrix and if you perform the following operations on an augmented matrix, the first one being, let's say, if you interchange two rows, the second one being multiplication of a row by a non-zero constant. And the third one is addition of a constant multiple of one row to the other row. So all these three operations, or all these three rules or three row operations, when applied to an augmented matrix, they do not change the solution of the linear system. And these three rules are known as elementary row operations. So they are known as elementary row operations. So basically, let's say there is a linear system S1, linear system of equation S1. And this linear system of equation S1 is row equivalent to another linear system of equations S2 if S1 can be obtained from S2 by a finite number of elementary row operations. So that is, if we apply one or more of these three rules to S1, and if we can ultimately reach or if we can ultimately produce the linear system of equations S2, then we can say that S1 is row equivalent to S2. And another way of saying it is that row equivalent linear systems have the same set of solutions, because as we saw earlier that the elementary row operations do not change the solution of a linear system. Alright folks, so that's all I had to talk about in this lecture. I'll see you guys in the next lecture.